Hi, this is an example problem having to do with the impulse momentum theorem. Take a moment to pause and read the problem here. Okay, so we're going to have a automobile accident here, and whenever we do a problem like this, we always have a before and after, and that kind of you can see from the equation, right? So the impulse momentum theorem, we can write it succinctly as J, the impulse, is equal to the change in momentum, right? But we also know that the impulse can be written as the average net force multiplied the time during which that force acts. And that's equal to the change in momentum, right? So momentum final minus momentum initial. Notice that we have a initial and we have a final, right? Initial and final in this case are always before and after the impact. Remember, impulse is like a very strong force for a short amount of time. So we're always going to go ahead and draw a before and after and start to gather information that we can use with the impulse momentum theorem. So I'm going to go ahead and do a before the collision and then a picture after the collision. And I need to go ahead and draw these pictures. Let me pause for a moment. So I've drawn a picture. You can see the before. The person's driving along. I'm not sure how they're going to be stopped in this accident, so I've put a wall there. And you can see after they crashed into the wall. Now, if you look at the equation for the change in momentum, right, as we saw before, we've got V final, V initial, right? So the before is V initial, and we want to write down what is the initial velocity of this automobile. Remember, this is a vector. It's one-dimensional, so we're going to just use the x-axis here, but we got to put the plus or minus sign in. And so we start with a positive 27 meters per second, positive x-axis, right? There's our initial velocity. What about the final velocity? So we know what that is. Final velocity, well, they are brought to rest, right, by the crash. So that tells us that V final in this case is just equal to 0. So we also know what the final velocity is. And finally, we need to know what the mass is if we want to calculate the impulse. And in this problem, we've been told that the mass is equal to 75 kilograms. That's the mass of the person in that automobile. All right, so now we need to calculate the impulse and the average force that act on the passenger in two different scenarios. In part A, she is not wearing a seatbelt. And in part B, she is wearing a seatbelt. So let's look at part A. No seatbelt. And in this case, we're going to calculate the impulse. Remember, impulse again is given by J, and it's equal to the change in momentum. And the change in momentum delta P, again, we can plug in P final minus P initial and put in mv for the momentum. So we can write the impulse like this. The impulse is going to be equal to mass times the final velocity minus the mass times the initial velocity. In other words, the change in the momentum. Now, in fact, we can factor out the mass if we want because it's common to both terms, or we can simply calculate this. Let's go ahead and look at our data here. Do we have any zeros? We do. So this is a 0. And that simplifies our equation a little bit. We get minus m times v initial. And let's plug in our numbers and see what we get for that answer. So I've plugged in the values there, and let's go ahead and compute that. Putting this into the calculator, it comes out to about minus 2,000 newtons times seconds. You might wonder why I put newtons times seconds. Well, a newton times a second is equal to kilogram meter per second squared times a second, which is equal to a kilogram, cancel one of the seconds, meter per second. And of course, here's your kilogram, here's your meter per second. So both newtons times seconds or kilograms times meter per second, they have the same units. Notice that there's a negative sign in the impulse. Remember, the impulse is like a big whack. Which direction was the car smacked from? Well, it was smacked from the wall, which is on the right-hand side, and so the wall pushed back in the negative direction. That was the impulse delivered to the car. Let's calculate what the average force is here. So if we consider the equation again here, notice that we can relate directly impulse with average force. So if I write this, I can say, okay, the impulse, it is by definition equal to the average net force times the time interval. And if we solve for the average net force by some algebra, we'll see that this is equal to J, the impulse, divided by the time interval. And so we can calculate the average net force during this crash. So we're going to put in minus 2,000 newtons times seconds divided by, now we need to divide by the time interval during which the crash occurs and this average force is applied. In case A, she's not wearing a seatbelt, so it's very short, 0.01 seconds. When we calculate this, we're going to end up with a force equal to negative 2.0 times 10 to the 5th newtons, or minus 200,000 newtons. Again, that's a negative sign because the wall pushed her back in the negative direction. Let's go ahead and write down the values. So for part A, we got the impulse is equal to minus 2,000 newtons times seconds, and we got the force is equal to the average net force minus 2.0 times 10 to the 5th newtons. All right, let's look at part B. This is wearing a seatbelt. And we're again going to be calculating the impulse, and we're going to be calculating the average net force. Are either of these two things the same? What has changed in this problem? Well, the time interval in this case, right? Time interval here is going to be a longer time. With the seatbelt on, you aren't just thrown forward into the dashboard and immediately stop in 0.01 seconds. You stop over a much longer time. Whereas with no seatbelt, right, delta t here was equal to 0.01 seconds. A really short time because you're just thrown into the dashboard and you stop immediately. How's that going to impact the values for J and for the average net force? Well, we want to calculate the impulse for part B. Again, it's the same equation. Change in momentum, mv final minus mv initial. And if we look at the picture again, it's the same picture, right? It takes longer to come to a stop, but same initial velocity, same final velocity. We're going to get the exact same answer here. Because all we're looking at is you started at 27 meters per second, and at the end you're at 0. And so that's going to come out to be exactly the same as what we had before. So notice that the impulse delivered, in both cases, it stops the car. It's the same value. How does that change the average net force? Well, let's use our equation. Same equation, right, for average net force. It's still equal to the impulse divided by the time interval. And in this case, the impulse hasn't changed. Still minus 2,000 newtons times seconds, but we've got a longer time interval. And so when we calculate this, we're going to get a different answer for the average net force, and this case is equal to minus 1.35 times 10 to the 4th newtons. So still a relatively large number, but much smaller than the previous one. Let's go ahead and write down our values for these two. So the impulse, minus 2,000 newtons times seconds, that's the same. The car was still brought to rest from the same starting speed in both cases. But the average net force, that is a much smaller number. And so notice there's a trade-off here, right? If you look at delta t, you can have a small value of delta t, which gives a large value of the average net force, or in this case, you can have a larger value of delta t, which gives you a smaller value of the average net force. Now, that means that the force is less if you can extend the impact over a longer time, and that makes you much less likely to get injured, because it's the strength of the force that causes your injury, not the impulse. One more part on this problem, we're going to go ahead and see what the acceleration is here in terms of g's. So to calculate the acceleration for a problem like this, I'm going to do it in part A and part B. The acceleration, average acceleration, is just going to be the average net force, Newton's second law, divided by the mass of the person. And so in this case, we've got minus 2.0 times 10 to the 5th newtons divided by 75 kilograms, a woman's mass. And we're going to get some number when we plug that in. It comes to minus 2.67 times 10 to the 3rd meters per second squared. That's a big acceleration. We can actually convert that into units of g's. You may have heard of g's, like an airplane pilot making a turn because of the centripetal acceleration experiences g's, and if there's too many g's they might pass out, right? Lots of g's of acceleration, bad for your health. Well, to do that we can just say simply 1g is equal to 9.8 meters per second squared. And if we calculate that, then we'll go ahead and see how many g's of acceleration this is. And I get a 272 g, roughly. I'm going to go ahead and just take the absolute value here so that we can get a positive number in g's. And of course the 9.8, the meters per second squared units canceled. So 272 g's, that's what we got there. Let's do the next one here. It's going to be the same thing. A average equal to the average net force divided by the mass. In this case we got a lower value, minus 1.35 times 10 to the 4th newtons divided by 75 kilograms. And let's go ahead and do our conversion to g's right away here. So 1g is equal to 9.8 meters per second squared, and we'll see how many g's we get here. This one comes out to about 18g. And so we can compare these as well. A g is an acceleration of gravity, right? And if you have a lot of g's, that can cause you to be really injured. Lower g's is better. So we can see certainly that much safer here is the seatbelt compared to no seatbelt, right? And it all comes down to this trade-off that I was talking about earlier between the time of the collision, the time during which the impulse is delivered, and the average net force, right? If you can increase the time, the average net force goes